Hello everyone. Welcome to Hydropower. Today in this lecture we will talk about the location of intake, non-pressure and pressurized intakes, general arrangement of intake, control of bed load and floating debris in RoR intakes. So let's start with introduction to run-of-river headworks intakes. In the context of hydropower generation and run-of-river headworks, the intake structure plays a vital role in diverting water from a river or stream to the power generation system. The design and operation of intakes vary based on factors such as location, water conditions, and project requirements. This lecture provides an overview of the different aspects related to RoR headworks intakes, including location selection, types of intakes, general arrangement, and control of bed load and floating debris. Location of intakes. When selecting the location for RoR headworks intakes, the flow rate and availability of water in the river or stream are major considerations. A key concept in this process is the flow duration curve, which illustrates the percentage of time that a particular flow rate is equaled or exceeded. Analyzing the FDC helps determine the most suitable intake location. For example, a point along the river where the flow rate is equaled or exceeded 90% of the time would be considered a reliable choice for an intake. In practice, this involves graphical analysis of the FDC to make an informed decision on the intake location. It's important to note that the formula involved is not a single formula but rather the graphical interpretation of the FDC. Non-pressure and pressurized intakes. RoR headworks can employ non-pressure intakes, which rely on gravity to direct water to the power generation equipment. The design of non-pressure intakes depends on factors such as the available head and flow rate. The hydroelectric power formula is a fundamental equation used to calculate the power output from such systems, as given, where P is the power output, ρ is the density of water, G is the acceleration due to gravity, Q is the flow rate, H is the available head, eta is the overall efficiency of the system. Pressurized intakes introduce additional complexities related to pressure conduits and water transport under pressure. In these cases, the energy equation, accounting for pressure head in addition to the available head, becomes crucial. The formula for pressure head in pressurized intakes takes into account the pressure difference, as given, where P1 is the pressure at the point of interest, P2 is the reference pressure, ρ is the density of water, G is the acceleration due to gravity. General arrangement of intake. The general arrangement of an intake structure involves various components designed to direct water into the system while preventing debris from entering. Two common components used are trash racks and bar screens. Designing these components considers factors such as water velocity and the size of debris to be captured. The appropriate opening size and spacing are typically determined based on engineering standards and empirical data. Trash racks and bar screens play a vital role in preventing debris from damaging or obstructing the power generation equipment. Empirical data and industry standards are used to design these components, ensuring they are appropriately sized and positioned to effectively capture debris while maintaining a desired water flow. Control of bed load and floating debris. Control of bed load and floating debris is another important aspect of RoR headworks intakes. To manage bed load, sediment basins are often incorporated to allow sediment to settle out of the water before it reaches the intake. The settling velocity of sediment particles can be calculated using Stokes' law, as shown below, where v is the settling velocity, g is the acceleration due to gravity, ρs is the density of the sediment particle, ρ is the density of water, r is the radius of the sediment particle, eta is the dynamic viscosity of water. To control floating debris, the design of trash racks, bar screens, or automated cleaning systems is based on factors such as flow velocity and the size of debris. These designs are typically derived from empirical data and industry standards to mitigate the risk of debris accumulation and potential damage to the power generation equipment. It's important to note that the design and calculations for bed load and floating debris control depend on specific project requirements, site conditions, and engineering standards. Consulting with experienced hydropower engineers and professionals is crucial to ensure the intake system is properly designed to operate efficiently and effectively control bed load and debris. Conclusion. In summary, RoR Headworks intakes are an integral part of hydropower generation. The proper design and operation of intakes are essential for diverting water from rivers or streams to the power generation system. Factors such as location, flow rate, and available head need to be carefully considered in the selection and design of intakes. Non-pressure and pressurized intakes serve different purposes, with pressurized intakes involving additional complexities related to pressure conduits and water transport under pressure. Trash racks, bar screens, and sediment basins are common components used in the general arrangement of intakes to control the entry of debris into the system. Designs need to account for factors such as water velocity, debris size, and settling velocity of sediment particles to ensure optimal performance and prevent damage to the power generation equipment. When it comes to controlling bed load and floating debris, calculations based on empirical data and adherence to industry standards are crucial. Consulting with experienced hydropower engineers and professionals is highly recommended to ensure the intake system is properly designed, efficiently operated, and capable of effectively controlling bed load and debris. For today, we will end up the lecture. We will come with a new video. Till then, keep on watching our videos and don't forget to subscribe our channel.